Talk about the enzyme reaction rate. This is basically how fast or slow the reaction is proceeding. And this is how many molecules or how much product is generated per time. And this can be determined by the substrate concentration. It can also be influenced by the enzyme concentration. So what does that mean? I want to really drive this point home. What does that mean? How can the rate of the reaction be controlled by the substrate concentration or the enzyme concentration?
Depends on if we have more substrate than enzymes or more enzymes than substrate.
Okay. Let's say we have lots of substrate. What's going to happen?
We're going to have to create more enzymes to accommodate that. Or we'll have more substrate left.
Okay, good. So how is that going to influence how fast, how much product is made? Just common sense, right? It's just the law of the more of something you have, the more likely you are to interact with it. Right? It's just available, just more available. Right? So if you have lots of substrate, we're going to bind it up to those enzymes. We're going to make more product more quickly. We're going to increase the rate of reaction. If we have more enzymes, again, we're going to interact with more substrate more often or more frequently. We're going to create more product. We're going to increase the rate of the reaction. So if we have lots of substrate or if we have lots of enzymes, if we have both, we increase the rates of the reaction. That is how much product is being churned out. All right, any questions on that? Sometimes it's a bit difficult to see. All right, another thing that affects the enzyme reaction rate is the affinity of the enzyme for the substrate. The affinity for the enzyme for the substrate. What does the affinity mean? What is affinity for the enzyme for the substrate mean?
How much an enzyme likes.
I think I'm hearing it perfectly said.
How much an enzyme likes it?
Okay, good. So how much the enzyme likes the substrate? Are they attracted to each other? Right? If they have lots of affinity, if it has a great attraction for that substrate, we're going to have the reaction proceeding more quickly and we're going to speed up the rate. If there is less of an affinity, we're going to slow down the rate of that reaction. And finally, there's temperature and pH. Again, as we mentioned earlier, most enzymes have an optimum temperature and an optimum pH, meaning that they are at their peak activity under certain conditions. So if you remove, let's say, pepsin is an enzyme that's found in the stomach. Let's say you remove it from that acidic environment in the stomach, it will no longer function optimally. Okay? It needs to be in that acidic environment where it is exposed to hydrochloric acid, and that will help to activate it. Any questions so far? Okay, now let's talk about the regulation of enzyme activity. Now, why do we have to regulate enzyme activity? Why is it important for us to regulate an enzyme?
Where it needs to be.
Okay, so it's going to keep the body certain levels where they need to be, which ties into homeostasis. Good. Any other answers on that one? Why do we want to regulate the activity of an enzyme? We don't want an enzyme to be functioning continually, do we? No. All right, we want it to be functioning when we need a certain product or substrate, and we want it to not be functioning when we don't need that. That's going to tie back into the efficiency of the body. If we need something, we want it to turn it on, we want to make it, and if we don't need it, we want to turn it off and not make it anymore. Okay, the body does not want to spend energy making some sort of product that it does not need. Okay, it's very efficient in that way. So there are 4 mechanisms by which enzyme activity is regulated, and we'll talk about each of the 4 of them. So the first one is allosteric regulation, right? Allosteric regulation. And this is basically where we have two different sites on the enzyme. There is a regulatory site and an active site. Okay, and there's some sort of modulator that binds to this enzyme and basically changes the shape of the active site. So the modulator or some sort of molecule will bind to the enzyme. It will bind at the regulatory site, and in doing so, it will change the configuration of the active site, which will then change the enzyme's activity. So this could speed up the enzyme, this could slow down the enzyme, this could make it active, make it non-active, and so on and so forth. But whatever that modulator did, when it bound to the regulatory site, it had an effect changing the active site and changing something about the activity of that enzyme. Okay? And so in this way, we can regulate the enzyme's activity. We can turn it off when we don't need it on. We can turn it on when we do need it to be working. And this is allosteric regulation. Okay. Secondly, there's covalent regulation. Covalent regulation. So covalent regulation is one that we're going to see very, 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 very commonly throughout this course. Okay, there's an enzyme, enzyme A, so some sort of enzyme. We'll talk about what that enzyme is in a minute. It is going to catalyze the formation of a covalent bond where it puts some sort of chemical group onto this enzyme. Right, so let's not get confused here. So this is some sort of different enzyme, enzyme A. Its job is to add a covalent bond or add this chemical group to the enzyme in question, the enzyme we're talking about, the one we're trying to regulate. Okay, and in doing so, the enzyme's active site will somehow change. Right, so that covalent bond being bound to the enzyme, okay, is going to have some sort of effect on the enzyme's activity. It can increase it, it can decrease it, and so on and so forth. Alternatively, there is another enzyme, enzyme B, that is going to break that bond. It's going to remove that chemical group from the enzyme. And in doing so, it's going to have a reverse effect on the enzyme. Okay, so we removed that chemical group here, we removed that covalent bond, and we had a configurational change in the active site that either deactivated the enzyme or activated, whatever was the opposite of having, whatever the opposite of having the bond was. Okay, let's look at an example here. Now this chemical group is oftentimes a phosphate. We're going to see that a lot throughout this course. And the enzyme that was enzyme A in our previous scenario was protein kinase. Right, so protein kinase is going to add a phosphate onto this enzyme. Okay, and what we get at the end is this enzyme and phosphate complex. So I'll say that again. We had an enzyme here. Protein kinase is going to form a covalent bond between the regulated enzyme and a phosphate group. And what we end up with is this enzyme phosphate complex. It's phosphorylated here. Okay, and this can occur in the reverse. So a phosphatase is the enzyme that will cleave or break this phosphate, take away this, cleave this covalent bond between the enzyme and the phosphate. And what we'll get at the end is that regulated enzyme and the phosphate group split off. All right, now I want you to associate in your mind, anytime you see a protein kinase, anytime you see a kinase, this is adding a phosphate group. Okay, this can either activate that enzyme or it can deactivate that enzyme, but it's going to regulate it in some way that it changes its configuration. All right. Similarly, anytime you see a phosphatase, that is cleaving or cutting or taking away the phosphate group there, or dephosphorylating it. We're going to see that when you look at the creatine kinase pathway in muscle physiology. We're going to see that when we look at glycolysis, and so on and so forth. So please bear this in mind. This is very important. All right, the third method or mechanism of regulating enzyme activity is feedback inhibition. Feedback inhibition. And this is something that we touched slightly on last time when we looked at negative feedback loops and negative feedback inhibition. Okay, so in this sequence of events, or this reaction at the bottom of the screen here, we have a substrate A, right? It's going to be converted to product B via enzyme 1. Product B will become a substrate for enzyme 2, and that will give us product C. Product C will then become an enzyme for a substrate for enzyme 3, and that will give us finally product D. Okay? So the way this reaction is proceeding, we have 3 enzymes and we have 4 substrates / products. Now, the step where product B or substrate B is converted to product C is called the regulated or the rate limiting step. Does anyone know why we want to call that step the rate limiting step? Does anyone know what the rate limiting step means? So this basically means that the more formation of product C that we have, the more we are going to feed back to inhibit enzyme 2, which is going to cease the production of product C. Okay, so if we have lots of C floating around, we're going to feed back, inhibit enzyme 2, which will stop the reaction from proceeding at that step. This is usually the slowest step of the reaction because then the products of that step are going to build up more quickly, and that's the step we really want to regulate. So I'll go over that again. All right, so the rates of E1, enzyme 1, and enzyme 3 are constant. Those are not being regulated. Okay. The step that we are going to regulate is enzyme 2. And this is dependent on, what is this dependent on? The regulation of enzyme 2 is dependent on the concentration of what? C, good, product C. So the amount of C that is produced will determine whether E2 is activated or whether E2 is inactivated. All right, I hope that's clear. Any questions on that bit? Any questions? All right, let's look at another example here. Still feedback inhibition. In this scenario, we have, again, same 4 substrates and 3 enzymes. But the concentration of product D is what is regulating enzyme 1. Okay, who wants to explain what this means in their own way? Right, so given the example we just saw, I'd like someone to explain this different scenario in their own words. I'm getting someone clear their throat. You can take some time to think about it, and then it doesn't have to be right. Okay, so I'll give you a minute to discuss this with someone. So you feel comfortable with what's going on, and then you can share. Question?
I saw your email by the way, but I still actually do this account.
That's fine.
Yeah, that's what I figured.
Because once A goes to B, no matter what, B's can go to C and C's going to go to D at the same rate. But that concentration at the end is still
Okay, anyone ready to volunteer? Or to explain this to us?
All right, so in enzyme D, I believe, well, I don't know if these enzymes are so strict, but in D, there's too much. It's that D is eliminating the amount of like action that's going on in D. So if there's too much D, then there's less D going on.
Okay. So there's too much D. So you said D is regulating the activity of E1. So there's too much D, will turn off E1. Right, that is correct. So what else is true about this reaction? Anyone want to add anything else? What else is true about this reaction?
after the first reaction, the rates between B to C and C to D are going to be the same no matter what until we figure out the concentration of B. That's what will control the first reaction.
Perfect, thank you. So the rate of B, C are constant. It's until we get to D that we're going to determine whether or not we want to turn on or turn off E1. Right? Does everyone get that? So B and C will progress as normally. Even if there's too much B and there's too much C, it's not until we get to D that we make that decision to inhibit E1, which turns the entire cascade off. Ready? So as a result, the conversion of A to B is the rate limiting step. If A is converted to B, everything else will proceed. Right? A to B is that one area that we can limit this entire equation. But as long as we've made B, there's no holding it back now. It's going to have to proceed. All right. Any questions on that? Okay. Now the last example of regulation here is feed-forward activation, and this is very rare. Right? This is not found very commonly throughout the body. And this is basically where we have some sort of we have a chain of reaction or a sequence of events in a chemical reaction, and there is a product that is influencing an enzyme that is upstream from the location of that product. Okay? So I'm going to give you a minute to look at this reaction and to come up with some conclusions about what's happening. Right? So you can explain what's happening in your own words. And how is it different from feedback inhibition? Okay, so I'll give you 1 minute to do that.
Feedforward predicts what's going to happen. Your body predicts.
Yeah.
So your body sees the concentration of heat, and it's going to start producing an enzyme. Well, it can be big too. It all depends on the concentration of heat. I don't know.
What?
I'm not.
I'm not an expert.
Oh, but
You're the Bible that way. And then forward, if these activated, if he is going to inhibit heat resistance, and then
Okay, anyone ready to share what's happening in this scenario and how is it different from feedback and conditioning?
I think it's a positive feedback loop instead of a negative feedback loop, and I think it's dependent on what's in front of it versus the one behind it, or like, just again.
Okay, so this is an example of a positive feedback loop, all right, where we're trying to activate something else that's downstream. What else?
It's saying that there's not enough B, so then it wants to add more. So like in positive feedback loop, it wants to keep adding more. They're kind of like you did the example of the contractions during labor. So it wants to add more. So then I don't know if I'm explaining this right, but for it to get to B, for E3 to be activated.
Right. So we're going to increase the rate of E3 just to increase the flow of what's happening. Right? We want to potentiate this. Very similar, like Ariel said, to the example with the contractions. Okay, so LH is going to start. We have estrogen, which is being released from the ovaries, is going to increase even more LH. So that's just going to potentiate or augment what's already going on.